Hi everyone, I'm Sulagna Dasgupta. I'm a final year econ PhD student at the University of Chicago. And today I'll talk about my paper, Communication via Hard and Soft Information. So this is a paper about strategic communication. Many economic interactions involve one party trying to communicate strategically to another. One of the ways in which such communication can be categorized is if it's verifiable or unverifiable. Verifiable is where you can back up your statements with evidence, which can then be called disclosures or hard information. Unverifiable is where you're allowed to make any statements, but you can't prove them. In other words, that would be cheap talk or soft information. So traditionally, the literature has, by and large, analyzed these different forms of strategic communication in isolation. However, in the real world, arguably people have the option to communicate using cheap talk in nearly all situations, whether or not they have verifiable evidence to disclose. So in this paper, I introduced the possibility of using cheap talk in verifiable disclosure settings. Whether and how allowing for cheap talk makes a difference in verifiable disclosure games is the focus of this paper. So here's the roadmap. I'll first introduce the model, use an example to illustrate the equilibrium structure, introduce my main results one by one while running through that example, and finally I will conclude. So here's the model. The baseline model is a relatively standard single-dimensional verifiable disclosure model. So we have a sender-receiver game of strategic communication. We have a sender that privately observes a one-dimensional state distributed on some compact interval according to a publicly known prior capital F. For today's talk, we assume capital F is atomless. The sender can verifiably disclose this state to a receiver. As is standard in much of this literature, we assume that the sender's payoff depends only on the receiver's posterior mean of the state theta through the continuous payoff function capital U. Again, for this talk, we are going to, for simplicity, assume that this payoff function U has no flat regions. So now suppose in addition to verifiable disclosure, the sender can also send cheap messages, as highlighted. Note that the cheap talk messages can possibly play a role only if a disclosure is not made. Otherwise, the receiver just sees the state directly. So in equilibrium, and we are going to focus on PBEs. So in equilibrium, the receiver forms a posterior belief about the state. Posterior mean is the only thing that's relevant, as I said, which we denote by small s. And that would be based on the sender's disclosure plus cheap talk messages sent, if any, in equilibrium, which we denote by M, as highlighted. So now we are going to introduce an example. So as a concrete example, think of a job candidate, the sender, looking for a job in a politically polarized sector such as media. His private information is his political leaning, left or right. So the x-axis here plots leaning towards right in the figures, and the y-axis the expected probability of hiring of the candidate. So the figures depict various cases. The first is a highly polarized media sector, arguably reflective of the current media landscape. So there, the more of an extremist you are, the more your chances of hiring by media companies on your own side of the aisle, giving rise to the V-shaped hiring probability function. The second one is an example of a moderately polarized media sector. So you're not hired if you're neutral, right at the middle, but neither if you're an extremist. So if you stand clearly on one side of the aisle, but are middle of the road within your own side, that's when you maximize your chances of getting hired, giving rise to the two peaks in hiring probability on the two sides of the dip at the center. That's the second picture. By the way, in all of this, I assume the prior to be uniform on -1,1, so there's a lot of symmetry. So we'll look at the structure of equilibria using these examples. So note that in any equilibrium, there can be just one payoff for all non-disclosure types, because every cheap talk message must fetch the same payoff in equilibrium. So let's take the payoff function on the left. So we want to see if V, the payoff level depicted in the figure, can be an equilibrium non-disclosure payoff level. So given any such V, what is the set of non-disclosure types? It's the set of types with disclosure payoff lower than V, the gray set in the figure. So note that in this case, for any V, the non-disclosure set, the gray set, it's an interval. So whatever the posterior means with cheap talk, let's say those are θ1 to θn or whatever number of posterior means using cheap talk, those must lie within that interval owing to the interval structure of the non-disclosure set for this type of payoff function. So therefore, the payoff at any of those posterior means θ1 to θn, they fall short of V, as we can see from the figure. So if V is a proposed equilibrium non-disclosure payoff level, the extreme types within the gray set, they will choose to disclose. So therefore, such a V can never be an equilibrium. It can never be an equilibrium non-disclosure payoff level. So in other words, unraveling, which is full revelation in every equilibrium, must occur in this case, regardless of whether cheap talk is available. Now, I will go to my main results and continue running with this example. So first result is that, like the previous insight, which we saw from that example, when generalized, that's what gives us our first result, which characterizes unraveling for all priors. So that's my theorem 1. Unraveling occurs for all priors if and only if the payoff function U is strictly quasi-convex. So there's a well-known result by Milgram and Grossman, which says that unraveling occurs for all priors if the payoff function is strictly monotone. That uses an almost identical setting, except two differences, important differences. One is that there's no cheap talk in their setting, and also they restrict to monotone payoff functions. And in that setting, they give this necessary, sufficient condition for unraveling. So I see our theorem 1 as completing this characterization, and I think this also brings out the essential force which leads to unraveling in these settings, both as illustrated by the Milgram/Grossman result and my result. And that essential force is that extreme types are better. That's the essential feature of quasi-convex payoff functions, which leads to unraveling for all priors. So now let's move on to our second result, which basically gives necessary and sufficient conditions for cheap talk to prevent unraveling. So now for that, we turn to the more intermediate polarization case, which we saw in the example towards the beginning. So note that by symmetry, for any potential non-disclosure payoff level V, the non-disclosure mean is 0. That's by symmetry. So that's plotted with the red vertical line down the middle of the figure on the right-hand side as a function of any proposed non-disclosure payoff level V. So without cheap talk, non-disclosure is never possible in equilibrium with positive probability, because non-disclosure mean is this lowest, it gives you the lowest payoff, so every type finds it beneficial to disclose. In other words, unraveling happens if cheap talk is not available. So now consider the following. Fix a potential non-disclosure payoff level V. So the non-disclosure set is again the gray set in the figure. That's the set of types with payoff weakly lower than V. Now conditional non-disclosure, if I were to declare truthfully as a sender that I'm on the right or left, what would be the posterior means? They would be the black dots as shown in the figure, let's say. But this does not constitute an equilibrium because the payoff at the black dots is too high, as we can see from the figure. So the non-disclosure set won't remain the same. More types would want to hide than shown in the gray set. And this is exactly where the role of cheap talk comes in. Now, because we have cheap talk, instead of truthfully declaring right or left after non-disclosure, as I just said, the sender can mix the two messages, which brings the posterior means closer towards the unconditional non-disclosure mean, as shown with the red arrows. So the red arrows are like, I have a right, left message and right message, but now I can mix them to bring the posterior means closer to the positions of the red dots, which actually constitutes an equilibrium. The red dots are equilibrium posterior means here, which are possible because of cheap talk. So taken together, what does that show us? It shows us that unraveling does not occur if and only if cheap talk is available in this example. As before, this example also generalizes. So cheap talk can prevent unraveling, by which I mean that there exists a prior such that unraveling occurs without cheap talk, but not with cheap talk. If and only if the payoff function contains what I call an M shape, which I'll define in a moment. But I hope it jumps out from the figure that in this moderately polarized example, the payoff function is in fact M-shaped. It's an M shape right there. That's what the payoff function looks like. And formally, basically, if the graph of the payoff function has these 5 points highlighted in the figure, such that connecting them gives us an M shape, then I'm calling it containing an M shape, and the boxed definition is just a formalization of that idea that this payoff function has to have a region where it goes up, down, up, down. That's basically the idea of an M shape. So to give a little bit of an intuition for this result, why is an M shape payoff function necessary and sufficient for preventing unraveling? So for that, let's understand what do we want. What do we want from such a payoff function which would prevent unraveling? So we want unraveling to occur without cheap talk and not occur with cheap talk, which would mean that on the one hand, we want non-disclosure to be really bad if we cannot create further separation within non-disclosure types. Once we have, like, one subset of types has chosen to hide their evidence, but at the same time, we want it to be want such a payoff function to be able to also profitably separate the non-disclosing types in some way, which would allow cheap talk to prevent unraveling. So the first purpose is the purpose which is served by the dip in the middle of the M shape. So for unraveling to occur without cheap talk, what role that dip serves is that that's like a very low region. So for an appropriately, the very low region of the payoff function. So for an appropriately constructed prior, the non-disclosure mean will remain close to that dip in the middle, always, regardless of the non-disclosure payoff level V. So that's the purpose of having that low region for middling types, moderate types. So formally, what we show is that for cheap talk to be effective, we need at least 3 disjoint intervals of low types for some non-disclosure payoff. More intuitively, we should think of the 3 intervals as 3 distinct categories of low sender types. I'll explain why in a moment. So in our example, let's see what these 3 categories are. So in our example, these 3 categories of bad types are neutral, right extreme, and left extreme, as highlighted in the figure. So what you do using cheap talk is selectively pool different categories of bad types together, so that because these intervals are disjoint, as I said, they come across as a better type in expectation a posteriori. So we can combine different categories of bad types to come across as a better type, which lies somewhere in the middle of the bad types. And that's exactly the motivation behind the M shape. So here what happens is that the sender pools the near neutral and extreme types, near neutral and extreme left for one message, and near neutral and extreme right for another message, and then he can mix those also. So that's what the sender does to come across as moderate, partisan in expectation when using cheap talk. So that's how cheap talk prevents unraveling. So our next result basically asks that, okay, unraveling is one way in which preventing unraveling is one way in which cheap talk can make a difference. When does cheap talk make a difference more generally? And we show that cheap talk almost always expands the set of equilibria. in a sense in which I make it precise. I will just make it precise in the next slide, but I will not have time to discuss this result more in detail. So basically, let me just state that. So the result says that for nice enough payoff functions, the set of priors for which either unraveling occurs or without cheap talk, or cheap talk expands the set of equilibrium payoffs, is dense in the set of all priors over the state space, like or Borel probability measures over the state space, even only if the payoff function does not have flat regions above the minimum level. So it's basically the purpose of this result is to give a sense that cheap talk very often makes a difference in outcomes in general, not just in preventing unraveling. And finally, let's see what is the effect of cheap talk on sender payoffs. And basically, the one-line summary of that is that cheap talk helps the sender whenever it helps him reduce disclosure or prevent disclosure. In other words, the less the disclosure, the better of the sender. That's our final result for today's talk. So again, let's go back to our examples. So we begin by observing that cheap talk can both help and hurt the sender. And we are going to illustrate that using an example. For that, let us add another scenario to the settings that we have considered. And that scenario is a very conscientious media sector, let's say, where the more neutral you are, the higher your chances of hiring. That's the figure on the extreme left. So I will show that in this case, existence of cheap talk actually hurts the sender. Note that staying completely silent, so we are running with the left-hand side case. So staying completely silent, neither disclosing nor sending any cheap talk message is an equilibrium in this case. And the reason is symmetry. As shown in the figure, if the sender stays silent, by symmetry, it comes across as the highest type, right the middle type. Again, the red dot is the equilibrium posterior mean. That's the center type. And the gray set, which is the entire type space in this case, is the equilibrium non-disclosure set. So the sender earns the highest possible payoff, regardless of type, in that equilibrium. Hence, no type has an incentive to deviate. So staying silent is an equilibrium which doesn't require cheap talk and earns the sender his highest payoff. So now we will see that cheap talk, when there's cheap talk, any V weakly lower than the highest level is an equilibrium non-disclosure payoff. So consider any lower V as shown. Again, the gray set is the non-disclosure set for that V. Again, if after non-disclosure, the sender were to truthfully disclose his leaning right or left, the posterior mean conditional on the left and right message would be the black dots. As shown with red arrows, mixing can then be used to bring the posterior means closer together, in particular to the red dots, so as to create an equilibrium, just like we saw before. So such a V is always an equilibrium non-disclosure payoff. So in this case, the existence of cheap talk makes the sender weakly worse off compared to the best equilibrium without cheap talk, in which he gets the highest possible payoff with probability 1. Now let us turn to the moderately polarized case, which we looked at earlier. In this case, cheap talk helps the sender. Let's see why. We saw that in this case, unraveling would occur without cheap talk, in which case interim payoff of each type is just its disclosure payoff. But we saw that non-unraveling equilibria exist, in which case each type earns weakly more, and by equilibrium conditions, the non-disclosing types earn strictly more. So cheap talk improves the sender's ex-ante payoff over the best and only equilibrium without cheap talk, which is full disclosure. Finally, the V-shaped case. In this case, cheap talk makes no difference. So that observation that cheap talk can both help and hurt actually helps us make sense of our next result, which is our last result, which is that the non-disclosure sets are nested across equilibria, with equilibria featuring lower disclosure being better for the sender. This is true whenever multiple equilibria exist, regardless of whether cheap talk is available or not. So the examples we just saw, they allow us to interpret this result in the following way, which is to say that taken together with our observation that cheap talk can both help and hurt, we can conclude that cheap talk can both thwart and facilitate disclosure, and it helps the sender if and only if it thwarts disclosure. That is, helps him avoid harmful disclosure. So that was all. To summarize, this paper investigates, in the context of this particular simple and canonical model, to what extent allowing for cheap communication alters equilibrium predictions in verifiable disclosure games. It completes the characterization of Milgram and Grossman to give necessary and sufficient conditions for unraveling, which turns out to be strict quasi-convexity, and that does not depend on cheap talk. I also fully characterize conditions of when cheap talk can prevent unraveling, and that condition is M shape of the payoff function. More generally, I show that for a natural class of payoff functions, whenever non-trivial equilibria exist, cheap talk typically expands the set of equilibria. When comparing sender payoffs across equilibria, we see that the less the sender discloses, the better off he is. Moreover, the ability to use cheap talk doesn't necessarily help the sender. So the third and fourth point put together basically says that cheap talk can both facilitate or thwart disclosure, and it helps the sender to the extent that it allows him to avoid harmful disclosure. Thank you.